here's where we actually get to finish up and actually we do what I would call the fundamental theorem of calculus thing. What we did in the last little video was to calculate the work done around a little tiny rectangle going counterclockwise, and we got an answer that looked like that. Now the idea is I want to put two of these next together. So let's say here's our rectangle going counterclockwise, and I want to put another rectangle right on top of it, just like this. Now I'm going to calculate the work done around that one. It's going to have a similar kind of answer, but watch what happens. I go like this, I go like this, I go like this, and you can see that the bottom rectangle, the top of the bottom rectangle has a little piece that's calculating work going left, and the top rectangle on the same side has the amount of work on that same side going right, and so they cancel with each other. And what we get is the work done around a bigger rectangle that now looks like this. Well, what we're going to do is start stacking these. So I put one like here, like this, and that goes away. I put another one below that, and it goes away. So what we're going to do is put a whole series of rectangles all the way over to the edge, like that. So this one's going all the way to the edge. Just that little slant, I'm not going to have to worry too much about that. Same thing as in Calc 1. This one has a little slant, but I'm not going to have to worry about that. And everything in the middle, all the work in the middle cancels. So what we're really getting here is the work done around the edge of this thing, and that's what happens when we add up the amount of work going around each of those little rectangles. We wind up getting the work around this big long strip. What happens if I put two strips next to each other? And do again counterclockwise. This goes up like this, going counterclockwise, going counterclockwise, going counterclockwise. But the strip on the left goes up, and so this part that's going up cancels with the part of this that's going down. And so when I put two of these strips next to each other, what we get is the amount of work done going along a much bigger strip. If I put another one next to it, the stuff in the middle all cancels with each other, and I get this, and we go all the way to the right. Right, we go like this, and everything in the middle all cancels. And this is all going to cancel, this is all going to cancel, this is all going to cancel, this is all going to cancel. What we're going to get, right, since everything on the inside all cancels, what we're going to get when we add up all the work done around the strips is going to be all the work done around the entire edge. By the way, what happened on the inside, it's called telescoping. We've talked about this, right? It telescoped when we actually stack them up from bottom to top, and then it telescoped again when we stack them up from left to right. So what we get here is that the work done is the sum of all the little work done as estimated this way is going to give an estimate of the work done around the whole curve, as long as we agree to go counterclockwise. Now what happens here, right, remember this is an estimate, is that the smaller delta x and y get, lots and lots of little good things happen, but the work done along each side is actually much better estimated. The estimate that we actually use for the difference quotients, those get much better. We get actually much closer to the edges, so everything gets better as long as delta x and y, delta x and delta y keep getting smaller and smaller. If we take the limit, like that, two things happen. Number one, we're going to get the exact work done all around the edge. Right? We eliminated all the errors by taking that limit. What we're going to get here is a double integral. Right? That's the double integral. That's the definition of the double integral. We're going to get integral sign instead of a sum, an integral sign instead of a sum. We haven't thought of this as being a roof, but when we try to calculate the integral, it's going to wind up being the roof. This can be delta x, delta y, or dx, dy, or dA if we like. What am I supposed to put for limits of integration? Usually what they do is they call the curve C and the region inside R. So R is just going to be the inside of that closed curve that goes around the edges. And this is the statement of Green's theorem. but you can see that the overall technique was very, very similar. You do a calculation on the inside, try to be as precise as you can, involves derivatives, and then when you start stacking up stuff, everything telescopes, and when you take the limit, you get a double integral here and a line integral here. That's why Green's theorem is true.